So let's continue. So in the first problem that we just solved, I want to mention that here. So you can see here that we try to use the image charge Q to replace the surface charge distribution sigma b, right? So the reason why we can do this is because of what we calculated before for the conductor case. So for the conductor case, if you compare the surface charge distribution for this problem and the problem of a conductor, the only difference is that the factor here is chi e over chi e plus 2 smaller. So that's what motivated us to use a single point charge to replace this surface charge distribution. And we know for sure that if we place a point charge below, then this charge will have the identical effect as the surface charge on this xy plane. And also, if we want to study the effect below, like what's the E field below, then the E field produced by this surface charge will also likely similarly be reproduced by us point charge d distance above this plane. And so both two regimes should be solved automatically by this point charge. And what we are not sure is that if this potential distribution on both sides will give us the correct boundary condition. And but that can be checked by taking the derivative of this scalar potential V on both sides. And the difference of the different derivative should give us back the bound surface bound charge. And now we check that actually these two agrees. Then this means that indeed this should be the solution everywhere. So in the last session we calculated the P vector, and we find that it turns out the P vector is radially along this r direction. And now we also calculated the volume bound charge. The volume bound charge is the divergence of this P vector. And in the spherical coordinates, remember that you need to multiply the r square and times the pr and then take the derivative. So this r square and the r square here cancels, which means the r square pr is a constant. And then this that's why the bound volume charge is 0. And when we are calculating the bound surface charge, remember that because the bound surface charge is inside here, and it should be pointing outwards, the n hat should be pointing outwards the surface, so it should be negative r hat. So this is a subtle directional problem that you have to keep in mind. And then because the n hat is negative r hat, so there is an additional minus sign. Okay, so now what we obtained is the bound charge produced by this dielectric material, but we still don't know what's the free charge, because on this on this conducting sphere, there can also be a charge distribution, and so let's try to find out this bound-free charge. Now, to find out the bound-free charge, we can first obtain the I think we already obtained the electrical field earlier. So the potential we obtained in the last lecture is 1 over proportional to 1 over r, and the electric field we obtain is the gradient of this v. So it's r over r squared v naught r hat, and now the total charge at this surface of the sphere we can calculate by the Gauss law. So the E field is perpendicular to this surface of this conducting sphere, and we simply take a closed Gaussian surface that's slightly larger than this conducting sphere, and then we can get the surface integral, and it has to be the total charge enclosed, and so the total charge should be the total sigma times the area divided by this epsilon naught, and so this on the left hand side it should be E times the area, and on the right hand side is the total surface charge density divided area times divided by epsilon naught, and so this sigma total should be epsilon naught v naught over r. So this is here I claim that this sigma total the way that I'm writing the enclosed total charge to be a sigma total times area indicates that I assume that the distribution of this total charge is a constant. That is valid because imagine that here the let me see. Here, because the electric field is spherically symmetric everywhere, so if this electric field is not a constant, if the electric field is dependent on the angle, then we cannot do this, and you can alternatively instead of integrating over the entire sphere, you can integrate a smaller portion of this sphere, and you should be able to get the same result. So in that case, you will start working on this sigma distribution as a function of angle, but you will see that in fact this angle does not play any role, and because this spherically symmetric of the E field, the sigma total should be a symmetric and a constant over the whole surface. But we know that there is a bound charge below this surface. So over here, the sigma total consists of the bound charge and the free charge. And while on the above, there are only the free charge. So below and above, the free charge should be different. So let's calculate the difference. So above this surface is the same as the total, and below if it has to be 1 plus chi e. So below the surface, there are more free charge, but there are also bound charge that's canceling out the additional chi e of this free charge, and which makes the total charge a constant over the entire sphere. Now you can imagine that the problem can be tweaked a little bit. So instead of working on where here right now the sphere is right goes through the center, right, of this sphere. The dielectric material right goes through the center of the sphere. Well, what if say that it's not that accurate, and say that the dielectric material actually slightly above the center? So could you imagine that is this problem still solvable?
Well, it's solvable, but it's upwards.
Yeah. So imagine that in this case, you can see that the E field should be so the D field itself should be coming out of this surface, so something like so you can imagine that if it's off center, then it's possible that along this edge there might be some surface charge, which actually makes the problem a bit complicated, even though it might still numerically be solvable. Analytically, this is not an easy problem to solve. So you can also kind of see that it's actually hard to work in spherical coordinate for this problem. However, a similar problem might still be solved. So what I mean is, say this time, what I'm going to tweak is so if I have a dielectric material like this, then here we can still imagine that the P is still radially going out. So in this case, the P is still parallel to this edge, and because it's parallel to the edge, then in this problem there won't be any surface charge at the edge over here, or at the edge over here, and the problem is still possible to be solved. Okay, so next I want to discuss about the energies in the dielectric systems. So remember that we've discussed the energy stored in an electrical field using the equation over here. So right now, what I'm trying to do is to calculate the energy distribution, energy stored in the field, but also with the linear dielectric material. So the way that I want to motivate the final result is to look at the problem of a capacitor. So the problem of a capacitor actually simplifies our understanding. So for a capacitor, there is positive charge and negative charge, and then there is also V potential V difference between these two capacitors. Now, if we want to store the energies in this field, so here this in the field, the field. The field of a capacitor, if you still remember, is only between the two parallel plates. And now if you want to increase that energy, you have to move the charge from one side of the capacitor to the other side of the capacitor. And that the electric the charge should have to overcome a potential difference of V. So now to charge a capacitor, d work you have to pay for an infinitesimal charge q is V times dq, and V is by definition q over capacity times dq, and now if you integrate this equation, it gives q squared. So the total work that you need to charge up a capacitor is q squared over 2c, or you can write this alternatively as 1/2 cv squared. I think this you also get this expression from 2041, and now this is the case for a capacitor without any material inside. And remember that in the last lecture we just discussed the change to the capacity if we insert a dielectric material. It simply multiplies the capacity by epsilon r. And then this means that the work or the total energy stored in the field should also be multiplying this expression by epsilon r. And now, if we look at the alternative expression for this energy stored in the vacuum, we have, and it seems that's logical to simply multiply this expression by this epsilon r. That will be the energy stored in the capacitor field with the dielectric materials. Now, what we can do is simple rewrite. So here this epsilon times r is also equals to d, the displacement vector. So what's inside can be replaced by this d times e. So now the claim is that here instead of energy stored in the vacuum, the correction to the energy stored in the system is with the dielectric material is simply replace one of the E by the D. and this is the expression for the total energy stored in the field. And now this is simply some argument but it's not an exact proof. And to prove that, we have to carefully go through this derivation by a similar approach when we calculate the work stored in a vacuum in an electric field in vacuum. So last time when we calculate the work, we try to add infinitesimal charge a bit at a time. But right now, what we want to do is, instead of bringing in charge that includes free charge and bound charge, we have to include only the free charge, and the material will be polarized as we increase the free charge, and then the work will automatically incorporate the energy stored in these materials. So now if we follow this direction, so the infinitesimal d work should be can be expressed as this infinitesimal free charge times v. So that's our original definition of this work, and so we can rearrange these terms by noticing that the del dot d equals the rho free. Then we can replace the del rho free by this del dot infinitesimal change of d hat. Now we simply copy the rest, and now we use the integral by parts. So here this divergent operator is applying on the d vector, but we can pull this out to apply on both sides. So this is the term that's supposedly on the boundary of the surface of interest, and then we divide by a term that's applying the del operator to the v terms. And now the first term, because imagine that we are doing the calculation in all space, so the surface actually is at infinity, and at that place v has to be 0. So as always, the first term goes to 0 and vanishes. So only the second term is left over. So the second term, remember that the gradient of v vector is negative of E, and then simply means is, so here you can see that we express this dw in terms of displacement vector and the electric field, and now for a linear, but this is for a general case, and for a linear dielectric material, the d vector can be written as this epsilon times e. So this d that's operating on this d alone can be now we can do a small trick by doing the differentiation to the entire expression. So this is you can double check by doing the del operator to the both sides. Simply just simply because this del f square equals twice f del f. And now for we simply arrive increasing slightly the del w equals the del of the expression on the right, and then we realizing that we can actually drop the del on both sides. So then we arrived our final result. So remember that for this expression to be true, the integral have to be go through the all space, because we have to be let the we have to go to the edge where here this surface integral goes to 0. So the work here stored in, or the energy stored in the fields is d times E, integrating over all space for a dielectric material. Comparing to these energy stored in this vacuum, you see that these two can give slightly different results. So you might imagine, like you might wonder which one is correct or which one I should use. So in reality, these two expressions are both valid, but they are referring to different things. So the first one, the one that's here is referring the work that's needed to bring in the free charge piece by piece, and you observe how this bound charge will distribute itself accordingly when you add up the free charge. And the second one is to build up simultaneously both the free charge and the bound charge. And the difference is that the first term doesn't include the micro. So the second term actually doesn't include the. You can think of the spring energy that's stored in the dipole when you are trying to build up this bound charge distribution in the in the second process. So the second process here, this E, remember that is really the average E of all these materials. So we actually remember that we are always calculating the macroscopic case of this E field, and we didn't. We simply average out all these fluctuations of E that's possible in a dielectric material. And remember that the W, the work stored in a field, is not a linear according to E, but it's E squared. So the fluctuations in the E is not counted in the second expression. So to really count what's the energy that's stored in this spring or in this tiny fluctuations of this E field, we have to use the first term. So in general, the first term is larger than the second term because the dielectric constant is typically larger than 1. Okay, so let's try to calculate an exercise of applying this energy expression. So here this problem is we have a parallel plate capacitor, and maybe I'm not drawing great, but what I'm trying to say is that there is this slab of dielectric material, and now what we are trying to see is to see what's the force of this dielectric material due to the capacitor. So first we need to calculate the we need to first look at this problem, maybe not calculate the problem first. So naively thinking, this problem can be think of that now if you have a charge on both sides of the capacitor, for an ideal capacitor, the problem the E field should be pointing straight up. Or sorry, in this case it should be straight down. And now if you apply this, if you add additional dielectric material, then it seems that the force felt by this material should be only in the z direction, or the direction pointing below. And now you can but is that really the case? Because if that's the case, then this slab will not move and will stay still, right? Because it will be because it cannot move either to the left and the right, and but we also know that a slab will actually increase the capacity, so it will increase the energy stored in the capacitor. So as you move the slab right into this capacitor, you imagine there is an energy build up, and then if you take the gradient of this potential energy stored by the field, it has to be giving you a force, right? So this force has to be along this x direction. So there has to be some kind of force pushing the material, and the origin of this force is actually something that's we often neglected. So if we calculate exactly the field of a capacitor, it's strictly speaking not exactly pointing downwards, because there are edge effects, and so remember that the field lines there should be some field lines going out, and actually it's this kind of field lines that's responsible to pushing this slab along the x-axis. So imagine that this material is being polarized. So there is a so say that it's linearly polarized, and you can imagine there might be some negative charge built up on the top of this plate, and there are some plus charge built up along this bottom of the surface, and now this point plus charge will feel a force to the left, and minus because you can see that the E field is slightly twisted to the left, and similarly, if you calculate the field and look at what's the negative charge field on the left, on top, it should also be a force that's pushing this pushing the negative charge towards the left. So if you combine the effect together, then there must be some force, total force along the x direction, and this force is due to this fringe effect. So if we don't consider any E field along the x direction, then this problem then there should not be any force, and but in reality this fringing field is not easy to calculate because it's a problem that can only be solved numerically, and in reality what we want to do is to instead of solving this force produced by this fringing field, what we can do is to look at the energy difference in the two configurations where this slab is moved slightly to this left, so to move the dx to the left, and then calculate the potential energy difference. So if we calculate this d work dx, then we know that that must be giving us the force. Minus sign? Okay. So now we can try to calculate the I think you have a similar homework problem where you are supposed to calculate the capacity for the configuration where there are two kinds of dielectric materials, and one is having an epsilon r, one having epsilon r prime. So for you can actually solve that problem in the homework, and set epsilon r goes to 0 for one case, and then you should get what's the capacity of this problem. So in the end, you should arrive at a capacity that's here. Here, this L, I mean the length of this capacitor, and the X is the distance without the slab. and here this W is the width of this capacitor. So now we can you should be able to derive this capacity from your homework, and after you get this C, you can simply calculate the force by taking the derivative of x, and which gives you here we just derived that is q squared over c, and we should do a partial derivative of the entire thing, and that should be giving us now the C we just obtained above, and finally we can arrive the final result. So you can see that somehow even though this force is due to the fringe field that's very complicated over here, we actually didn't know anything about the fringe field, and we are still able to calculate the force exerted by this fringe field. So that's simply by calculating the energy stored in this E field. So try to think about this. I think this is the magic of this Maxwell's equation. So even though you don't know the field that exactly did the force to you, and by calculating the potential energy difference, you still know how much force that you feel due to this fringe field. We will skip this problem, but the idea of this problem is actually similar to this parallel plate capacitor is. So here this problem is simply looking at the a cylindrical capacitor. You can think of this as still a capacitor. And the nice thing about this problem is that here, if you apply a potential, if you apply, say that this outside is grounded, but if you apply some potential to one side, you will introduce some electrical field, and then this field can actually pull some oil or some dielectric material up from the surface, and then also because of the gravity, the oil will also go down, and then the field of the electrical force that grabs the oil up and will balance the oil's gravity that's pointing downwards, and it will reach equilibrium position, and you can actually calculate what is the height it will be by simply calculating the field stored in this electrical field. So I'll simply quickly go through. So right now we've already finished the chapters 2 to 4. So in chapter 2, we learned a little bit about the Maxwell equations and the relation between the charge density, the E field, and the scalar V. You can derive one from the other from these triangles. And in chapter 3, we learn some technique to solve for this scalar potential V. And in chapter 4, we simply add the dielectric material into the problem. So there are two different kinds of dielectric material. One is the permanently polarized material, and another is the linear dielectric material.